Here we have a problem involving double integrals. We're given a region omega, two-dimensional region that's bounded by the x-axis and the y-axis, and the part of the circle that lies in the first quadrant where x and y are both positive. Then we're asked to do a number of things. Make a sketch of the region omega, labeling all the curves that bound it. Describe omega in Cartesian and polar coordinates. And then calculate the centroid of omega. And we're given a little bit of a hint, use symmetry. Now remember, symmetry can save us a lot of time when available. Okay, so we've got the part of the circle that lies in the first quadrant essentially bounded by the circle and the positive x-axis and the positive y-axis. Okay, not a great drawing, but so basically our omega is a quarter unit disk that lies in the first quadrant. Now, have we labelled all the curves? Well, yeah, I've labelled the x-axis, I've labelled the y-axis, and I've labelled the circle. So I think that's enough for this part of the problem. Part B, describe the region in Cartesian coordinates. Okay. Well, this might, this is not as easy as it looks. Now, for Cartesians, what we want, you can either essentially draw a horizontal line going from left to right and see where that horizontal line enters the region and leaves the region. They're your bounding functions. And then move the curve up and down the y-axis. Or you can use a vertical line. So draw a line starting down here, going up through the region and go, okay, where does that line enter the region and where does it leave the region? And then you just sort of move it from left to right to get your inequalities on your x variable. Now to do that, I'm just going to, that's the way I'm going to do it actually. So I'm going to write this as a function for this part. You can see that y is non-negative. So I can actually write just this part of the circle like this. So in other words, y is a function of x up here. Yeah? So, if I go back to my picture, now you'd probably draw, you might be able to draw a new picture here. You can see that this vertical line enters the region at y equals 0 and it leaves the region at y equals 1 minus x squared all square rooted. Okay, so enters the region at y equals 0, leaves the region at y equals at y equals root 1 minus x squared. So they are the two bounding functions for the y. Now, I take this vertical line and I shift it from left to right. How far do I have to shift it to cover the whole of the region? Well, it would be between x equals 0 and x equals 1. Okay? So, there are your Cartesian coordinates representation. Now, what about polars? What about polars? Well, I'm going to draw another line starting at the origin and emanating outwards. So I'm going to start here and draw a curve that goes through the axis. Again, you might want to draw your own curve, another set of drawings here, but I'm just going to squeeze it onto this one page. You can see that that red curve crosses or starts entering the region at the origin. So we've moved 0 distance from the origin, so r would be 0 in this case. Remember, in polar coordinates, we've got 2 variables. R, the distance to the origin, and theta, where theta is the angle to the positive OX axis. Okay? So, we can see the red line already is basically enters at the origin. So the lower bound for R would be 0. The upper bound would be, how many units away am I when I hit this curve? 1 unit. Okay? And remember the angle to sweep out the entire quarter disk, the angle would be basically it'd be a quarter of a full revolution. So the theta would be between 0 and pi on 2. Okay, so we've taken a lot of time to write those coordinates out. Now remember, drawing a picture not only helps, well, basically it helps us understand the geometry of the problem. If we're going to be describing sets and describing regions, then we're going to need some good geometric insight into the problem, right? So we've done that. Let's use the formulae in part D to calculate the centroid. Now remember, the centroid is like a centre of area or a centre of a region, like kind of like a balance point, if you like. It's a special case for the centre of mass when you have basically constant density. Okay? So, there's a little hint saying use symmetry. Okay, so is there any symmetry in our disk? Yes, there is. In fact, that red line just conveniently happens to be a line of symmetry. So, where do you think that the centroid for that omega should lie? It should lie on that red line somewhere. In other words, x bar and y bar should be equal. Okay? So the centroid of omega will lie on this line, i.e. x bar equals y bar. Now, so what? Well, the idea is that if you know x bar, then you can immediately write down y bar. Okay, you only have to calculate one of the coordinates, not both of them. Once you have one, you have both of them. Okay? So, let's calculate x bar from this. All right, let's look at the denominator first. The double integral over omega. So physically, geometrically, what does that mean? It's the area. It's the area of omega. Now, if omega is a simple region, a very simple region like this, you can just calculate the area of that region just by using simple high school methods, right? Okay, so it's the area of a unit circle divided by 4. Okay, so it'll be pi on 4. Easy. No double integration required. Now for the top, for the numerator, yes, we might need some integration there. Now, we have the choice of either employing to actually calculate that double integral right down the bottom, through either Cartesian or polar coordinates, because you've got both descriptions. So what you would like to do here is choose the simplest case. I'm just going to use polars. Okay, you don't necessarily have to do that, but that's the way I'm going to do it. So with polars, we replace dA with r dr d theta. We replace x with r cosine theta and y with r sine theta. There's no y's here though. Okay, and the limits of integration are formed from these limits up here. Okay, so the d theta's on the outside, so we would have the theta limits on the outside integral. Okay, so now what you can do this a couple of ways. You can see a quick way of doing this is that you've got basically you're integrating a function of r times a function of theta. You've got r squared times cosine theta, and the limits of integration are constants. So you can actually split this up into the product of two single integrals. So you take that r and that r, and you combine them to get r squared. So essentially you're just taking two single integrals and multiplying them together. Now you can't always do this. Functions of one variable times the function of the other variable integrated with constant limits of integration is the prime way to split these things up. So if I integrate cosine theta, I'll get sine theta. If I integrate r squared, I'll get the following. So this is going to give me 1/3, and this is going to give me 1. Okay, so what are our centroids? Well, we can go back. It's this divided by this. Okay? So if you just rearrange that, you'll get 4 on 3 pi, and that's also equal to y bar by symmetry.